So my dear students, today we are going to discuss an important topic, and this topic is chemical equilibrium. This topic is slightly difficult for most of the students, and students face difficulty in this topic. So my motto is to make this topic easy in terms of understanding and in terms of clearing your doubts from your notebooks. Okay, so let's discuss about the chemical equilibrium. The word itself, chemical equilibrium, indicates about its properties. So in chemical equilibrium, we discuss about the chemical reactions under equilibrium. So what is equilibrium? So equilibrium is a state in a chemical reaction. So we can define equilibrium as a state of chemical reaction. You can say state or stage, both. A stage in chemical reaction or a state of chemical reaction in which the rate of forward reaction becomes equal to the rate of backward reaction, or I must write instead of giving symbol, becomes equal to the rate of backward reaction. So remember, equilibrium is a state in which forward rate of reaction becomes equal to backward rate of reaction, and this equilibrium, this state or this stage, is only possible in for a reaction that can proceed in both the direction, that is forward as well as backward. So equilibrium can only be achieved in reversible reactions, or the reactions that can proceed in both the direction, forward as well as backward. That is, reversible reactions are the reactions that can proceed in both the direction. Reaction that can proceed in both the direction. Both the directions, forward as well as backward. Forward direction, forward as well as backward direction. Backward direction. So this is the main definition about that, about chemical equilibrium. So reactions that can proceed in forward and backward directions achieve a state in which the rate of forward reaction becomes equal to the rate of backward reaction, and at equilibrium you will not see any kind of change. You will not see if a reaction is going through any change. You will not observe. So under equilibrium condition, so I must say that under equilibrium condition, condition reaction do not show any change, do not reveal any change. So all the parameters of the reaction, for example, of the reaction, for example, temperature change delta T, pressure change delta P, entropy change delta S, enthalpy change delta H, internal energy change delta U, concentration change delta C, it is concentration change seems to be 0. All the changes seems to be 0, means all the properties becomes constant. Seems to be 0. All the changes becomes 0, rather all parameters becomes constant. You will not see any change after equilibrium. Okay, now to understand equilibrium, I am just going to show you a picture. Through this picture you will able to understand what exactly equilibrium is. Suppose a school has circulated an advertisement. In this advertisement, the school is means calling people to come for admission of their students or for their wards. So the school has it in a hurry. We have limited seats about the admission. Suppose we have a school. Suppose we have a school and the school has 500 seats. School has 500 seats or 500 seating capacity for the students, and it is calling students for the admission. And the admission is on first come first serve basis. First come first serve basis. So what do you think? First come first serve basis. And suppose this town, we have a town. This town has a population of 4,000 kids. 4,000 kids. So the town has a population of 4,000 kids, but the student seats available at the school are only 500. What will you see? Initially, more and more kids rush to the school. Initially, more and more kids rush to the school for the admission. Rush to the school for the admission. And since it is on first come first serve basis, so the school will try to take admissions as much as possible. Now after some time, school will be filled with maximum seats. Now what will happen? So the rate of coming of students to the school will decrease, because most of the students, most of the kids are getting admitted to the school. So the rate of kids moving to the school will decrease. Kids moving to school will decrease, will go down. So, and after some time, and the school is filled with all the seats. Now school is filled. Filled seats. the school has filled all of its seats. Now which will happen? Now this will happen whenever a kid will move from a town to the school, realizing that all the seats are filled up, so it will move back. So at this time, the forward rate becomes equal to the backward rate, means the number of students moving to the school are getting back to their town. So the forward rate becomes equal to the backward rate. So this is how equilibrium setup. So an equilibrium has been set up. Equilibrium means now there will not be any change in the number of students or kids inside the school, and similarly there will not be any change in the number of kids in the town, because now the total kids left in the town after getting all the admission or after getting all the seats filled up in the school. So I will minus 500 from this, and the total kids in the town will be left with 3,500, and the total kids and in the school will be 500. So we will not go above beyond that, and this population gets constant, means the school population becomes constant and the town population becomes constant. Now whenever a kid will move from town to school, it has to move back to the town. So it's the state of equilibrium. Now the population of the kids at the town, population of the kids in the school are constant, but it doesn't mean that kids are not moving from town to school or school to town. But although they are moving, but there will not be any change in the number of students inside the school and the number of students or the kids in the town. So this is a state of equilibrium. This condition like this also happens in chemical reactions. So let's see how chemical reactions proceeds in such manner. For example, we have two reactants, A plus B, and A plus B are reacting to getting converted into C plus D. Initially forward rate means rate of consumption, rate of converting these reactants, rates of converting these reactants to the product is very high, means all maximum number of reactant gets converted to the product. So rates of getting reactant into the product will be almost 100%. So initially the forward rate is very high. Forward rate means rate of conversion of reactant to product. So forward rate is very high, and the backward rate is almost null, that is zero. None of it's just like that. In the initial stage, the students that are being the students that moves from town to the school getting admitted there, they are not coming back. Similarly, the reactant that is being converted into the product will not comes back to the reactant state, but after some time the product starts to coming back. The product slowly the backward rate starts to initiate slowly. So after some time the forward rate will decrease, and the backward rate try to increase a little bit. So with time some of the product will try to convert into reactant, into reactant, and rate of backward reaction will try to increase. Rate of backward reaction will increase slowly and steadily. So what will happen? So with time, rate of forward reaction So we can say that with time in a reversible reaction, so with time in a reversible reaction, rate of forward reaction will decrease, rate of backward reaction will increase. I'll call you later. So with time in a reversible reaction, so with time in a reversible reaction, rate of forward reaction decreases, will go down, but the rate of backward reaction will increase. And the rate of backward reaction will increase, and after some time the rate of forward reaction becomes equal to the rate of backward reaction. And after some time we can say that after some time the rate of forward reaction becomes equal to the rate of backward reaction. And the concentration of both the reactant and product becomes constant at that point of time. And under this condition, the concentration of reactants and products becomes constant. Or fixed. Means after that you will not see any decrease in the concentration of reactant or any increase in the concentration of product, means at the time of equilibrium. Okay, so this was equilibrium. You can also visualize equilibrium by this one example. For example, you can also come to conclude about the equilibrium position by this example. Suppose we have a slope. Suppose we have this mountain, and we have a vehicle going uphill. So we have a vehicle. Suppose this is a vehicle going uphill. So I must write down this. Suppose this is a vehicle. What will initially do you suppose? Initially, the vehicle will climb up comfortably. After that, the vehicle will try to face an opposing force, the gravitational force downward. So with time, as the vehicle moves uphill, an opposing force generate that will try to bring vehicle again to its original point. And with time, the opposing force becomes stronger and stronger, because the more you move above, the higher the gravitational field you will face. So at a particular time, or after covering a particular distance, suppose this vehicle has covered this much of distance. Suppose the vehicle has covered this much of distance, and it is you can say 2 kilometers or 2000 meters from the base, and you are left with suppose 500 meters. You are left with 500 meters, and the vehicle got stuck here. And at this point, all the vehicle is trying its hard to go forward, or the engine is moving continuously, or the vehicles or the wheels are running continuously in order to cover the left out distance, but somehow it is not able to do that, because the downward force is so strong that it is not making it viable for the vehicle to move up. So at this point, the vehicle has covered up to its maximum distance, and it has stuck. Now it is achieved an equilibrium state. So it can't move forward, and neither it want to move backward. So it has achieved the maximum. It has covered the maximum distance it can cover. After that, the distance left will be constant, and the distance covered will be constant. So at this point, it has covered 2000 meters, and the left out distance will be 500 meters. So you will not see any change in these two distance. Similarly, you will not see any change in any of the parameters at equilibrium in terms of reactant and in terms of product. So at equilibrium, all the properties of reactant and product becomes constant. Remember, they are constant, they are not zero. A product means pressure, temperature, color, density, concentration, all becomes constant for reactant as well as for product. So all these parameters are constant, or becomes constant at equilibrium for reactant as well as for product, Remember, these parameters will have their fixed value, but if I say change in parameter, or I write down the parameter more precisely, the change in parameter will be 0. You will not see any change, but it doesn't mean they have a 0 value. They have a constant value. I am again emphasizing on this statement. This statement is very important. Pressure change will be 0, temperature change will be 0, color change will be 0, density change will be 0, concentration change will be 0, but their magnitude will not be 0. There must be some pressure, there must be some temperature, there might be some color, there must be some density, there must be some concentration of each of the reactant. They must have some fixed value for reactant as well as product. But if you say will there be any change in pressure of the product at equilibrium? No, it will be 0. Will there be any change of the temperature of the product at equilibrium? No, it will be 0. Will there be any change in the color of the product at equilibrium? No. Will there be any change in the density of the product? No. Will there be any change in the concentration of the product? No. Will there be any change in the pressure of the reactant? No. Will there be any change in the temperature of the reactant? No. Will there be any change in color? No. Change in density? No. Change in concentration? No. There will not be any change, but they must have a constant value. So this is about what you say equilibrium. So equilibrium can also be plotted on a graph paper. So if we talk about the graphical representation of equilibrium, we can have a graphical representation like this. So I'm going to give you a graphical representation just in terms of equilibrium. So I'm going to draw the graph. I should select it from the drawing. Suppose it is a graph, and we have two variables, that is y-axis, and we have another variable called as x-axis. So we have x-axis. Oh, I have written it so badly. Axis. So y-axis represents the rate of reaction. Whether it's a forward reaction or a backward reaction, we have a rate of reaction. And the x-axis represent, or you can say, a time. So with time, what will happen? The rate of forward reaction decreases, but the rate of backward reaction will increase. So I am going to represent this point. A reactant is getting converted into product. So I must write reactant. So we are dealing with a reversible reaction. So a reactant getting converted into product for a reversible reaction, and we have achieved an equilibrium here. So with time, the forward rate will decrease. The forward rate of reaction, I must draw with another color. So this one. So forward rate will decrease. And it is the forward rate of reaction. It is a plot for forward rate of reaction. Forward rate of reaction. And similarly, I'm going to plot for the backward rate of reaction. So with time, backward rate of I must start with 0, because initially the backward rate of reaction will be 0. And after that, forward rate of reaction becomes equal to the backward rate of reaction. Forward rate of reaction becomes equal to backward rate of reaction, or you can say the backward rate of reaction. So these two lines will merge with each other after some time. So you have to merge these lines. If it is a plot between a rate of reaction versus time, then you have to merge it. So it is the line for, so I must indicate it with arrow, so you come to know which one is decreasing and which one is increasing. So it is forward rate of reaction, and it is decreasing with time, and it is backward rate of reaction, and it is increasing with time, and after some time they becomes equal to each other. So it is the plot for backward rate of reaction. Backward rate of reaction. So backward rate of reaction. So it is the line for backward rate of reaction. Remember, you have to merge it. So at this point of time, they both have a same rate. They both have a same value. So they both have a same rate. So it is, you can say, at this point of time when they meet with each other. So it is called time for equilibrium, or it will give you an equilibrium time. So it is the plot with respect to the rate of reaction versus time. So in rate of reaction versus time, the forward rate decreases, backward rate increases. They merge with each other and run in associated form. So forward rate becomes equal to backward rate. So it is with respect to rate of reaction. Similarly, we can have a graph with respect to concentrations. So the concentration, you can have a similar graph like this also. Like this, you can have, at any point you can meet. You can meet at further above point. you can meet at very low point. Okay, this point of merger can be at the upper side of the y-axis, can be at the lower side of the, or can be at the middle. It can be anywhere else, but and the moment they meets up each other will give you equilibrium, time to set up equilibrium, got it? So now we'll see about how concentration graphs are given in terms of equilibrium. So we'll discuss about the concentration graphs. So it was the rate graph. Now we'll discuss about the concentration graph. So here are the concentration graph for equilibrium. So I'm going to give the concentration graph. Here it is. It is a graphical representation, and I must write down here y-axis. Now this time y-axis is going to represent about the concentration. It is the concentration. What do you think? What will happen to the concentration of reactant? Will it go down, or will it increases with time? Obviously, concentration of the reactant will decreases with time. And here we have time. So here we have a reaction, reactant getting converted into product, so with time, concentration of reactant will decreases. So with time, concentration of reactant will decrease, while concentration of product will increase with time, and after some time it becomes constant. And concentration of product increases with time, because initially we had zero product concentration, but and we have only the reactant in our reaction chamber or reaction beaker. So with time, more and more reactant gets converted into product. So with time, more and more product will be formed. So with time, product concentration will increase while the reactant concentration will decrease. So I'm going to draw the plot again. So it is the concentration curve for reactant. So the concentration, so the time it becomes parallel to this x-axis. So it is parallel to x-axis. So I must not, rather I should draw it again. Let's check whether we have an option here. We do not have an option here. I have to means I can go like this. Oh, again. Okay. Got up to this, and after that I can draw a line. Yes. Now it becomes constant from this side, this point. So it is the concentration. This graph represents the concentration. I must indicate it by sign. It is decreasing with time. So it is the concentration of reactant. Concentration of reactant. So the concentration of reactant decreasing with time, and after that it becomes constant. There will not, you will not see any change after a particular time, and the concentration of product is increasing. Concentration of product is increasing. So I must draw a parallel line to the x-axis. So here. So and the moment these two means lines becomes parallel to the x-axis, that represents time, So here the concentration of a product is increasing, so I must indicate it by this arrow. So the concentration of product, concentration of product is increasing, and after this you will not see concentration becomes constant. So concentration of product is concentration of reactant, upper line, and lower line concentration of product, they both are now constant. Concentration of product, they both are now constant. So this point at which this point at which they becomes constant shows point of equilibrium. It shows that it is time for equilibrium. At this time equilibrium has set up. But this graph, I can't say that this graph will be of this type only. We can have more than this type of graph in concentration terms. For example, we can have a graph like this, where these two lines will run parallel to the x-axis after merging. This is also represent concentration versus time. So here the concentration of a reactant and product becomes, you can say, they run parallel to each other, get merged. So it is also equilibrium time. Similarly, we can have like this. It is also the equilibrium point. We can also have like this. We can also have this equilibrium point. So but just you have to see at where they have parallel orientation with respect to x-axis. They may cross with each other also. They may cross with each other, but they should run parallel to each other. They may run parallel to each other. So all these graphs represent equilibrium point. So it is equilibrium point, it is equilibrium point, it is equilibrium point, it is equilibrium point. The moment these concentration curves run parallel to the x-axis, these concentration curves may cross with each other. One may be above the other, one may be below the other, one may run in merge condition. So concentration curves can be of any type, but this rate curve will be of this type only. You always have to merge the rate with each other. Okay, so this is for up to this graphical representation. Now we are going to discuss some questions on the content we have learned so far. So my dear students, we'll apply the concept we have comprehended so far to resolve this question. So given here, I'll give you the question. Given here are 7 graphs. Now explain which one of the following graphs represents chemical equilibrium. Here F is forward direction, B is backward direction, C represents concentration, R represents rate. So the very first graph, that is this one. Just think about it. So Y is a rate axis. Y represents rate of the reaction. RF is forward rate of the reaction, and RB is backward rate of the reaction. So I must indicate here for your convenience, it is a forward rate of this. RF represents forward rate. rate, and RB represents backward rate. Backward rate. Now same here, forward rate, backward rate, forward rate, backward rate. These are a rate. So let's consider graph 1. I must take on the green one. So here the forward rate becomes equal to the backward rate at this point of time. When I'm going to drop the perpendicular normal. So this is the time interval. So at this I must write TEQ. TEQ. It is the time interval at which equilibrium has been set up. So this graph, that is 1, represents chemical equilibrium, because here the forward rate merges with the backward rate and the forward rate becomes equal to the backward rate at a particular time. And that time is called as equilibrium time. So RF here in this is equal to RB. So graph 1 represents chemical equilibrium. Okay, let's move on to graph 2. So in graph 2 we can see that we do not have any point on the graph where we have RF equal to RB. So here this line indicates that after some time forward rate becomes constant, here backward rate becomes constant, because RF represents forward rate, RB represents backward rate. So we do not have any point on the graph where forward rate becomes equal to the backward rate. So this graphical representation do not represent a chemical equilibrium. A state of chemical equilibrium is not being achieved in a second graph representation. I must cut down second. So a second graph is not representing any kind of chemical equilibrium. Now moving to the third one, for the third graph representation. Here also it is more or less just like a second graph, because forward rate is not being equal to the backward rate. No point on the graph represents forward rate becomes equal to the backward rate. So this graph also do not represents chemical equilibrium, because forward rate are very much different from the backward rate, although they are being constant after some time, but we do not look for the constant parameter of the forward and backward rate. Rather we look if they both are equal or not. So third graph is also not able to justify chemical equilibrium, because we do not have any point where forward rate becomes equal to the backward rate, because whenever forward rate becomes equal to backward rate, so you must have a point like this where forward rate becomes equal to backward rate. So forward rate merges with the backward rate. So it is representing chemical equilibrium. Okay, so it do not represent chemical equilibrium. It do not represent chemical equilibrium, because in terms of rate of the reaction, because this graph is between rate and time. So in terms of the rate of the reaction, rate versus time, we must have a graph like this. Okay, now moving to the fourth graph. The fourth graph is between concentration. So on the y-axis we have concentration, on the y-axis we have concentration, y-axis we have concentration, on the axis that is time. So CR is the concentration of a reactant. CR represents the concentration of a reactant. Concentration of a reactant. And CP represents the concentration of product. CP represents concentration of product. Got it. So here after a particular interval of time, both concentration of reactant and concentration of product are constant. They become constant. They are not being changing with the time. So after a particular time, at this time where we have dropped a perpendicular from the point at which concentration of reactant becomes our concentration of reactant and concentration of product are constant, at that point of time I have dropped a normal, and this represents TEQ. So it is time or to achieve chemical equilibrium. So this point represents equilibrium. This graph represents very well equilibrium. Although concentration, both concentration of reactant becomes equal to concentration of product, but we do not have to worry about whether the concentration of reactant is greater or less than or equal to each other, but we must see whether it is a constant parameter with time or not. So after a particular time they must be constant concentration of reactant, so we can have a graph like this. Similarly, after a particular interval of time, concentration of reactant becomes constant and concentration of product becomes also constant. So at this point of time, we have chemical equilibrium. So this is the time at which we can have a chemical equilibrium. So I must write down TEQ. So it is equilibrium time. So this graph also represents chemical equilibrium. Similarly, 6th graph also represents chemical equilibrium, because after a particular interval of time the concentration of a reactant becomes constant and the concentration of product also constant, although they have different concentration. Concentration of product will be like this, concentration of reactant will be like this, but they are being constant. From the 7th graph, the concentration are not being constant. These are the concentration of reactant and these are concentration of product. They are not being constant, rather they are varying at every point of time. So this graph also do not represent chemical equilibrium. So my final answer will be graph number 1. Graph number 1 explains chemical equilibrium. Graph number 4 explains a chemical equilibrium. 5 explains chemical equilibrium, and 6 explains chemical equilibrium. In 4, 5, and 6, graph 4, 5, and 6, graph 4, 5, and 6. It is a graph between concentration and time. So it should have a constant concentration of both reactant and product, irrespective of the fact that whether these lines cross each other, they intersect with each other, they become parallel to each other, or they merge with each other. We do not have to see about that, but we have to see whether these two curves becomes parallel to the time, concentration becomes parallel to the time or not. While in case of first, second and third, these are the graphical representation between rates of reaction and time. So in rates of reaction time, we have to see whether these two curves meet with each other or not. So the curve in which we have both forward rate meeting with the backward rate represents chemical equilibrium. So our answer will be, so I'm going to write down the answer here below. So our answer will be graph number. So graph 1, graph 4, graph 5, and graph 6 represents a state of chemical equilibrium. Represents the state of chemical equilibrium. So this was all about a simple question. Okay, now we'll see some more questions. So we just comprehended the state of equilibrium through graphical representations, how with the help of graph we can understand about the equilibrium state, or how we can represent the equilibrium state or equilibrium phase of a chemical reaction. Now we'll see about the characteristics of chemical equilibrium state. Now, how equilibrium state is different from other states or stages of a reaction. So we'll see about the characteristics of the equilibrium state. Equilibrium state or stage. So we have following points regarding the equilibrium state or stage. So first point is that we all know that at equilibrium at equilibrium, the forward rate of reaction, forward rate of reaction is equal to the backward rate of reaction. Backward rate of reaction. Rate of reaction. Okay, so this was the basic and utmost important point. And second, now equilibrium can only be achieved in a closed system. Equilibrium can only be achieved in a closed system. In a closed system, we can only achieve equilibrium in a closed system because we want all the things together to move forward and backward. For example, if you have calcium carbonate, for example, if you have CaCO3, calcium carbonate is also called as quicklime. So suppose we have calcium carbonate, it generally exists in solid phase, and you placed calcium carbonate in open as well as closed vessel. Now look, we have this open vessel, open system, and now we have this closed system. So what will happen? This CaCO3, when you heat up CaCO3, when you bring CaCO3 to high temperature, then it will start to decompose. It will start to decompose into CaO plus CO2. Since CO2 being gaseous in nature, it will escape the system because the system is open. Now you cannot go backward direction because one of your component has left the system, so you cannot merge CaO with CO2 to again reproduce CaCO3. So we cannot achieve equilibrium in this state, because for equilibrium to and fro both directions should be equally possible. But if in case we have CaCO3 in a closed vessel, and now we are going to heat up, and it again produces CaO plus CO2. Now CO2 cannot escape because the system is being closed, so CO2 can react with CO, again produce CaCO3. So equilibrium can only be achieved in a closed vessel, because if we have a closed vessel or closed system, then we have all the components intact with us, and they can react to reproduce again the same reactant. So equilibrium can only be achieved in a closed vessel. If you have open vessel, you cannot achieve equilibrium state. Now the third is macroscopic properties are constant at equilibrium. So macroscopic properties that can be visualized at a large. For example, concentration, pressure, color, density. So macroscopic properties are constant or fixed, constant at equilibrium. So at equilibrium, concentration of all the reactant and the properties of all the reactant and product remain same. So at equilibrium, I must take a folder. So at equilibrium, the concentration of reactant and product becomes constant. Becomes constant. Similarly, other variables, macroscopic variables or macroscopic properties, will also be constant. For example, density, color, and all these. So now, fourth point, equilibrium can be achieved in from either direction. So equilibrium can be achieved in from a forward direction as well as backward direction. It is also an important point. So I must say that equilibrium can be attained. Equilibrium can be attained or can be achieved. Achieved from either direction. From either direction. This means that, suppose I'm talking about the formation of ammonia by Haber's process. So if we take this N2, this is a gas, plus a 3H2, again a gas, and slowly and steadily they will react with each other in presence of iron, that is a catalyst, and molybdenum, that is a promoter that enhance the action of catalyst. So with time, more and more ammonia will be formed. So that will be twice NH3, and that is also a gas. And the reaction is exothermic. Delta H will be negative. Okay. And now with time, after some time, some of the ammonia will try to dissociate back into the reactant, and after a particular time, when equilibrium has been attained, so forward rate, that is formation of ammonia, becomes equal to the decomposition of ammonia. At that point, you cannot have change in the concentration of ammonia or the change in the concentration of nitrogen or hydrogen. So at equilibrium, the formation of ammonia is equal to the decomposition of ammonia, because initially we have the forward reaction, and later on we have the backward reaction as well. So at equilibrium, I must write, at equilibrium, the formation of ammonia is equal to the decomposition of ammonia of NH3, or I can also write down, I must take off to a closer level of NH3, decomposition of NH3, that is gas. So we can also say that at equilibrium, I must write EQ, the disappearance of a reactant is equal to the formation of the reactant. Formation of the reactant. Okay, so initially we are observing that the equilibrium has been attained in just like a forward direction, attained by after some time after the formation of ammonia. Equilibrium has been achieved after the formation of ammonia, and after some time we can have a sufficient amount of ammonia. Now the ammonia will start to decompose and will reproduce the reactant and after some time the formation of ammonia becomes equal to the formation the decomposition of ammonia. So here equilibrium can be achieved by forward direction. We have achieved equilibrium in the forward direction. Now let us if the equilibrium can be achieved in the backward direction as well. So now I have taken ammonia, I have taken only the product ammonia, and I have closed this ammonia in a closed container. Now you will see that ammonia will start to decompose. Ammonia will start to decompose into nitrogen and 2 gas plus hydrogen H2 gas. Now the equilibrium has been achieved by taking the product. Initially we had achieved the equilibrium by taking the reactant. Now the equilibrium has been achieved by taking the product. Now so this point explains that equilibrium can be achieved from either direction. If you take reactant and forms product, then after some time the product will decompose and again come back to their reactant state. At that point of time the forward rate of reaction becomes equal to the backward rate of reaction, and we have attained the equilibrium. Now if you have taken the product and if you start decomposing the product, then after some time the reactant will combine and again reform the ammonia. Here you are observing you have taken ammonia in the closed container and you are decomposing ammonia. So after some time the ammonia decomposition will decreases, rather formation of ammonia will take place, and at this point the formation of ammonia becomes equal to the decomposition of ammonia. So equilibrium can be achieved in either direction, so whether it is a forward direction or a backward direction. So this was the basic points about the equilibrium, basic characteristics about the equilibrium state. So now equilibrium can be of 2 types depending upon the phase of the reactant and product. Depending upon the state of reactant and product, equilibrium can be of 2 types: physical equilibria